Dear all, I am Dr. V. Malati, Associate Professor, Department of EC, SR University, Varangal. Today's video lecture is on EEG signal acquisition and processing. It is simulated in Google Colab. I have written the code in Python. We will get an output of noisy signal versus filtered EEG signal. We will have the graph of time in second versus amplitude in microvoltage. Normally in biomedical signals, we will take the amplitude in voltage level. But for EEG, it is in microvoltage because supposing ECG signal, we have to place the electrodes around the muscles of heart. So in heart, the movement of blood will be seen. That is why the amplitude of the signal will be more. But in case of EEG, the electrodes are placed in the scalp. So movement of blood will not be available there. Therefore, conductivity will be stopped so that the EEG signal will be of very low in magnitude. That is why we are taking the signal in microvoltage level. In the output, we will get the output noisy signal versus filtered EEG signal. So next one, so the graph is drawn versus time and second against amplitude in micro voltage, and we get the time domain analysis also. We will measure mean value, variable, and then RMS value. Once again, we will get the filtered EEG signal in time domain. So it's a graph of time in second versus voltage in microvolt. So I am going to share the screen. So I will simulate the code in Google Colab. So this is what the output we are getting now after simulating. So I will see the noisy versus filtered EEG signal, amplitude in microvoltages, time in second in x-axis, the time domain analysis of filtered EEG, that is mean value around 1, mean 1 value 1, variance 2038, RMS value 45.167. So again in time domain we are getting the filtered EEG signal, time in second versus amplitude in microvoltage. So I am going to explain the code line by line. Import numpy as np. So Python code is taken from the library, that is import Python library from numpy, that is np. Then import matplotlib.pyplot as plt. So wherever we see plt, that means we are going to plot the graph. So graph means we can draw the graph of one parameter versus another parameter or histogram or box plot. So all the output in terms of graph we will get. So for that the matplotlib library is taken from the pyplot module. So it is important. In the same way, signal module from this IP library can be imported. But For this signal, there will be more functions available, but in this program, we need only butter and filter functions. So, these two functions are downloaded, that is imported from the signal functions. So, first one, simulation parameter. Fs is equal to 250. Now what is Fs? It is sampling frequency, the rate at which these samples are taken per second. That is sampling frequency. Then time equal to np dot a range 0, 10, 1 by Fs. That means 10 seconds duration. So the x-axis is time and it starts from 0 and ends at 0. This 10-second time duration is divided into uniform intervals. Now, in what way it is segregated? Now, step size. So, in between 2 points, what is the interval? It is equal to 1 by Fs. So, 1 by Fs means 1 by sampling frequency 250. 1 by 250. So, yes, a total sample of 250 into 10, that is 2500 samples are taken. So 1 by 250 is equal to that value is indicating the interval between first point and second point. So if you count into 10, they have given 10-second duration. So 250 into 10, 2500 samples. Next one, create simulated EEG signal. EEG consists of multiple frequency bands. So we know that alpha, beta, theta, delta. And here these four are the components of EEG signal. But here theta signal is not considered because theta signal is appearing in the infant only. That is why infant case we have not considered, only normal adult signal we are considering. So alpha is equal to, delta is equal to 50 into NP sine 2 pi 2t. That is 2 hertz for delta. So there will be a frequency range for all the waveform components. For delta it is 2 hertz and for alpha it is 10 hertz. Beta is equal to 20 hertz. But amplitude is different, 50, but for alpha it is 30 sine 2 pi 10t. So omega is equal to 2 pi f. So angular frequency conversion is made here. Then beta is equal to 20 amplitude sine 2 pi f is equal to 20 hertz. And then what these lines generate. So wave type, first one is delta, it is 2 hertz. Then the amplitude is 50 microvolt. So it is what it is indicating the brain state of deep sleep. So it is in adult only. Next one, alpha. So alpha means it is of 10 hertz amplitude, 10 hertz frequency and then 30 microvolt amplitude, and it is appearing in the relaxed brain state. Then beta is 20 hertz and then its amplitude is 20 microvoltage and then it is appearing in the active thinking of brain state. So all these three come from adult only. So what is the formula used? Actually all are varying. AC component only. Waveform means AC only, not DC. So AC will be represented as A sin omega t. So A sin 2 pi ft. A means amplitude. And then clean EEG. How we will get? So all together it is the combination of delta, alpha, beta. This creates a realistic EEG signal containing multiple frequency components. and then add noise. It is 50 Hertz power line plus random noise. So 50 Hertz power line, why we are taking? So we are placing the electrode so that current only flows. So we have to consider 230 volt AC 50 Hertz. So for our domestic AC range, that frequency only we have to consider. So the interference coming from this 50 Hertz is known as power line interference. And then random noise. Due to our muscle contraction or expansion, some small amount of noise will appear, and that is known as random noise. So here noise is equal to 40 into NP sine 2 pi NP pi 50 t plus 25 into NP random dot RANDN len t. Now what is the meaning for this line? Two types of noises are added. First one, power line interference. So as I have already told you that 50 Hertz sinusoid. So common electrical noise. Then random noise. Normally for all we have to take the reference noise such as white Gaussian noise. So random noise is a white Gaussian noise. It is taken as reference. It simulates muscle artifacts and background noise. Now, noisy EEG is equal to clean EEG plus noise. So, this is the signal on which we are going to apply any process, not clean EEG, because we will not give the clean EEG directly. Now, Butterworth bandpass filter. So pass band is equal to 0.5 Hertz to 40 Hertz. So pass band, so the frequency components below 0.5 Hertz will be removed, and frequency components above 40 Hertz will be considered as high frequency noise so that they will be removed. So, the frequency components lying between 0.5 Hertz to 40 Hertz will be considered as useful, and they carry the required information. So, bandpass filter means we should have lower cutoff frequency and higher cutoff frequency. Lower cutoff frequency is equal to 0.5 Hertz. Higher cutoff frequency is taken as 40 Hertz. And the order of the filter is equal to 4. So order is equal to 1 normal, nothing, 2, 3, actually they are higher order filter, but still it is fourth order filter means it will filter very smoothly. The filtering action is very steep. That is why higher order filter is considered here. And that is the order of filter is taken as 4. The Nyquist frequency is equal to half of the sampling frequency. Why we are doing means lower cutoff frequency divided by Nyquist. So whatever the value we obtained here will be putting the denominator of lower cutoff frequency, because we have to normalize the lower cutoff frequency. In the same way, higher cutoff frequency also we have to normalize so that the final value will lie in between 0 to 1 only. So normalization in the same way is going to happen for high equal to higher cutoff frequency divided by Nyquist. So next one, why we are taking 0.5 and 40 Hertz range for bandpass filter. EEG frequency range lies between 0.5 and 40 Hertz. So all waveform components of EEG for that minimum value is 0.5, maximum value is 40 Hertz. That is why 0.5 to 40 Hertz are taken. The range is taken. It removes the DC drift less than 0.5 Hertz. And then power line loss of 50 Hertz. So this also will be removed so that it is considered as noise. Then Nyquist criteria 0.5 into Fs. So Fn, that is Nyquist frequency, is equal to Fs by 2. 250 by 2 is equal to 125. Then low equal to low cut. So low cut we know, Nyquist we have already found out. So we have to apply here. So Butterworth function requires frequencies between 0 and 1. That is why we are normalizing the frequency. Next one, B comma A. So butter, open bracket, order, comma, low comma high, then B type is equal to band. So butter means Butterworth filter. Order is 4, we know. Low already determined the value of low. In the same way, high value already determined. Butterworth type of filter is equal to band pass filter we have adopted here. So that this calculation will give you the numerator of the filter coefficient B, denominator of the filter coefficient P. So filtering action is nothing but we have to generate the filter coefficients. These will filter the signal. Then filtered EEG, it is equal to filter B comma A noisy EEG. Now what is the meaning? Filter means it will give no phase distortion, no delay. So filter will be very smooth so that we will get the clear EEG signal. We know that B numerator of the filter coefficient and A denominator of the filter coefficient all are applied over the noisy EEG. Then plot noisy versus filtered EEG. Now what is the meaning? PLT dot figure. Figure size is equal to 12,6. So 12 is the width of the graph and 6 is the height of the diagram, that is graph. Then PLT dot PLOT time comma noisy EEG comma label, it is equal to noisy EEG. So alpha is equal to 0.6. Then PLT dot PLOT time comma filtered EEG label filtered EEG, line width is equal to 2. Then x limit. So what is the x limit? Means the x axis is limited to 0 to 5. X lim stands for x axis limited to 0. So starting value of x axis is 0. 0 is the starting value, 5 is the ending value of x axis. Then PLT dot x label. So in x axis time in second is mentioned. In y axis alpha in amplitude in microvoltage. Then PLT title. So for this diagram, noisy versus filtered EEG signal. So PLT dot legend. So why it is used? It is used to display the legend box on a plot. So in the previous cases we have shown the graph but not in box. But here we are using the box. That is why the command PLT dot legend, and PLT dot show means the output is visualized. And then next one we have to do time domain analysis. Mean underscore value, it is equal to NP dot mean filtered EEG. The average amplitude should be very close to 0. That indicates baseline level. And then variance value, it is equal to NP dot where filtered EEG into 2. It measures signal spread higher variance, that means variance is higher means higher brain activity. So we have to get the variance value more as far as possible. Then RMS underscore value is equal to NP dot square root NP dot mean filtered EEG into 2. So this RMS gives effective power of the signal. And now what is the equation formed by this line? RMS is equal to square root of 1 by capital N sigma x square. So higher RMS, it is showing the stronger neural oscillations. then print time domain analysis of filtered EEG. So we have to print this one, and again it has to show the calculated value of mean value, and then print variance value what here from this expression calculated, that figure will be printed here. In the same way, RMS value from this formula, what calculated, what value calculated, it will be mentioned here. And then plot filtered EEG in time domain. So PLT figure, the figure size is equal to 12, 4. 12 with 4 is the height. And in PLT dot plot T, filtered EEG. So how we have a x-axis is time, y-axis is filtered EEG. So we know that time in second in x-axis. We know that EEG signals are mentioned in amplitude in voltage. So here amplitude in micro voltage, and x-axis is limited to 0 to 5, y-axis micro voltage, and finally you give the title to this plot filtered EEG signal in time domain, and then plot dot show. So we have to visualize the plot. So this is the noisy versus filtered EEG signal. The blue signal is noisy signal and the orange signal is filtered EEG signal. So the calculated value, time domain analysis of filtered EEG, mean value 1.29, and then variance value 2038, RMS value 45. So once again in time domain, filtered EEG signal will be obtained. The graph is drawn, time in second versus amplitude in micro voltage. So in this case, so first one what we did, we have to download, we have to import the library functions from the module. So here we are mainly drawing the graph showing the signal. That is why Matplotlib, that library will be downloaded from the imported from the pyplot module. So we have to use because all the signals are in sine function, sine signal function. That is why we have to take butter and filter both the functions from the signal library we have to take. And then sampling frequency is equal to 250. So sampling means number of samples taken per second from the signal. So time is equal to NP dot A range. So it starts from 0, ends at 0. And in between, how many components are there? I mean, how many samples are there? 250 into 10. So 2500 samples are present from the 0 to 10, so that we can tell that the interval between 2 points is very small. So we have to create the EEG signal. So EEG signal contains 4 waveform components, number alpha, beta, delta, theta, but theta is not taken into account because it appears only in the infants. So we consider the subject is adult. So alpha, beta, delta waveforms we are considering here. So delta is equal to 50 into NP dot sine 2 pi 2t. So 2 is the 2 hertz range for the delta, and then magnitude is 50, and then alpha is of 30 microvolt, and then sine 2 pi, f is 10 for alpha. Then beta 20 microvolt amplitude, sine 2 pi, 20 is frequency of beta. So final next one we have to what is the clean EEG? Clean EEG is the combination of alpha, beta and delta. So once again theta is not considered here because it appears only in infants. And then that clean EEG we cannot process because before giving to the input of the filter, we will definitely the signal will have be added with the noise. So where from this noise come? There are two types of noises. Number one, random noise, and number two, power line interference. So random noise means it is coming from the environment. So normally the reference noise is high frequency. That means frequency is high, amplitude is low. So this low amplitude of noise will not overcome the original biomedical signal. That is why amplitude should be very less for the noise. But frequency normally noise means high frequency noise will be considered. So white Gaussian noise will be taken. So mean value is 0, variance is 1. So finally, what this will generate a delta waveform of 2 hertz with 50 microvoltage. But what it indicates, it is the brain state of deep sleep. In the same way, alpha means 10 hertz with 30 microvoltage amplitude, and what it indicates, it is the relaxed state of brain. And then beta is of 20 hertz signal of 20 microvoltage amplitude. Actually, it is showing the active thinking of brain state. So next one, clean EEG. So clean EEG means all the combination of delta, alpha and beta. This creates a realistic EEG signal containing multiple frequency components. And then as I have already told you that the signal will not be raw signal, it will be added with the noise before going into the filtration. So noise is equal to 40. So 40 is the amplitude and sine 2 pi f is the frequency of the power line, because our domestic line power line is 230 volt AC. So that is why 50 hertz is taken. Why AC 230 volt 50 hertz we are taking means we are providing the electrode on this scalp. So once if we provide install or place the electrode on the scalp or some other place, immediately electrical signal will flow. So that is why 50 hertz we are taking, and then 25 is the amplitude of the random noise. So random noise type is white Gaussian noise, and then RANDN. So random numbers will be generated, but LENT means whatever the process we are applying on the original signal, the same thing will be applied on the noise also. So length, what is the meaning? We have taken the original signal from 0 to 10. In the same way, the length of the time interval for the random noise is also between 0 to 10. And once if we apply the sampling on the signal, the same sampling process is going to be applied on the noise also. So sampling frequency, what we adapted here, if it is 250, the same 250 is applicable to the random noise also. So finally, we will get the noisy EEG signal. So EEG signal, clean EEG, we know already we have. In addition to the two types of noise, in general noises, so noise means interference plus Gaussian noise. And then we have to apply to the filter. So filter means here we are taking the order of fourth order filter for smooth filtering. So steep filtering will be done, happening. And then lower cutoff frequency, higher cutoff frequency for band pass filter. So in between the signal components in between 0.5 to 40 hertz will be allowed into the filter. And the Nyquist frequency is equal to half of the sampling frequency. So for sampling means it is applied for converting analog signal to digital. So for digitalization, the sampling Nyquist criteria should be fulfilled for the sampling process. That is why we have to normalize the frequency, lower cutoff frequency and higher cutoff frequency, so that the final value lie between 0 to 1. So low equal to lower cutoff frequency divided by Nyquist. Nyquist already we have found out. Lower cutoff frequency we already know 0.5. In the same way, high equal to higher cutoff frequency we already know 40. Divided by Nyquist also we have already determined half of the sampling frequency. With these values we have to find out the filter coefficients so that it will perform the filtering on the signal. So filtering coefficients means B comma A. These will form the filters. This will form the numerator and denominator of the filter coefficient, so that we will get the Butterworth filtered signal. So order 4 we know already. Low we have determined, high we have determined. Butterworth filter type is band pass filter. So that we will get, and then once again filtered EG will be applied on fill to function, so that fill means it will give clean EEG signal. So filtered EEG signal okay, but still it will be clean by applying fill to function. So we will be having the calculated value of this after simulation. So with this we conclude the simulation process. Thank you. Ah.